This video focuses on the grain size distribution of soils. The objectives for this lecture are to describe laboratory methods for developing that are used to develop a grain size distribution. The second objective is to develop a grain size distribution. And then third, you should be able to determine the coefficient of uniformity and the coefficient of curvature from the grain size distribution curve. Before we get into the details, I'd like to just give a brief explanation of why we care about the grain size distribution. One reason is we use the grain size distribution to classify soils. And this grain size distribution and the soil classification are indicators of the engineering soil properties. One example would be a sand that is well graded. So it has a large distribution of grain sizes. And so what we can gather from that, some of the engineering properties, permeability, how fast water flows through the soil. Well, the soil would be pervious. Second, shear strength. If it's a well-graded sand, generally they have excellent shear strength properties. And then the compressibility. How easily does the soil compress when compacted? And for a well-graded sand, that compressibility would be negligible. There are a couple of common laboratory methods used to determine the grain size distribution. The first method is a sieve analysis. That is described in detail by ASTM D6913. And then there's also a hydrometer analysis, and that is described in detail in ASTM D7928, where ASTM stands for the American Society for Testing in Materials. The sieve analysis is used to develop the grain size distribution for soils that are greater in size than 0.075 millimeters. So these are sands and gravels. The hydrometer analysis is used to determine the grain size distribution for those materials that are finer than 0.075 millimeters. A couple of reasons why we want to characterize the grain size distribution for the finer materials is determine the clay size fraction. That combined with the plasticity index, which we'll talk about in the future, it can be used to compute the activity, which provides an indication of the clay mineralogy. And second, the gradation of silt and clay sized fractions is an important factor in determining the susceptibility of fine-grained soils to frost action. So in areas where you get the ground freezing in the winter, when water rises and comes up towards into the zone that can freeze, when that water freezes, it can expand and cause damage to structures. So there's a couple of areas where we would be interested in the hydrometer analysis to look at the finer materials. As stated previously, the sieve analysis is used to characterize the grain size distribution of coarse-grained soils, that being sands and gravels. On the left, I'm drawing a stack of sieves. These are cylinders like little pots with the bottom having a wire mesh at the base. We stack them with the larger opening sieve at the top and the smaller opening sieves at the bottom. And I'm drawing here a cross section of one of the sieves, and so you can see at the base you have the wire mesh. There are a set of standard sieves that we will use when performing a sieve analysis so we can appropriately characterize the distribution of grain sizes. So we have a sieve size, which is designated by a number. On the left, you see these numbers, number 4, number 20, number 60, number 200. And each of those numbers have a corresponding opening size. So right now I'm listing the standard sieve sizes that are used to get the distribution for sands, grain size distribution for sands. A number 4 has an opening size of 4.75 millimeters. A number 10, opening of 2 millimeters. Number 20, 0.85 millimeters. Number 40, 0.425 millimeters. Number 60, 0.25. Number 100, 0.15. Number 140, 0.106 millimeters, and the number 200, 0.075 millimeters. Anything smaller than 0.075 millimeters, we cannot see a difference. We can't differentiate grains when they're smaller than that. And materials that are smaller than 0.075 millimeters, we call those fines. They consist of silts and clays. Anything that's larger in size than 0.075 millimeters will either be a sand, as long as it's in this 4.75 millimeter to 0.075 millimeter range. If it's larger than 4.75 millimeters, it's going to be a gravel. Eventually you'll have cobbles and boulders as the sizes get larger. The measurements that we make when performing a grain size distribution. Again, we're going to place the soil in these sieves at the top, on the top sieve, and we're going to shake it for about 10 to 20 minutes. We need to know the mass of the soil that we place in the sieves, so that's the sample dry mass. And then when we are done shaking it, the soil, we're going to empty the sieves into a dish and measure that mass, and we're going to develop the cumulative mass retained on each sieve. To determine the percent finer by mass for each grain size, we'll use the following equation where we have the percent finer by mass is equal to 100 times the quantity 1 minus the cumulative mass retained on a given sieve divided by the dry mass of the soil. We'll go work on an example quickly. So given that we have a soil sample with a dry mass of 100 grams, and then the following sieve information. So we've taken this 100 grams of soil, placed it in the sieve, shaken it for 10 or 15 minutes, and now we are going to record the results from that test. So we have our sieve size, our sieve opening, the cumulative mass retained on each given sieve, and then our calculation, which will be the percent finer by mass. First, we'll list our sieve sizes, ranging from a number 4 down to a number 200 sieve. Go ahead and list the sieve opening size. And then, having conducted the test, we made the following measurements. We had nothing retained on the number 4 sieve, 20 grams of soil retained on the number 10 sieve. Then once we add the material from the number 20 sieve to the soil that was retained on the number 10 sieve, we end up with 40.6 grams. So that's the cumulative mass. Okay? And then we continue to do that. In performing our calculations for the number 4 sieve, 100% of the material was passing the number 4 sieve. We can see that 80% of our material passed the number 10 sieve using the equation that was provided previously. 59.4% passes the number 20 sieve, and again we list just listed using the same equation, listing the percent finer by mass for the other sieve sizes. And that's all there is to performing a sieve analysis. The next thing we want to do is we want to plot our results. And so let's look at a plot of this sieve data. In plotting the results, we'll generally use some software to do that. It's not convenient to plot by hand, so I typically use Excel to plot my Sieve Analysis results. Using that data, we plot the grain size on the horizontal axis, and we use a log scale to do that. And on the vertical axis, that's where the percent finer by mass is plotted. So this is an XY scatter plot in Excel. You can see the data points are from the table that we just put together in the previous slide. And then we use a smooth curve to connect the points in our grain size distribution. A visual inspection of the grain size distribution can allow us to see whether or not we have a well-graded or poorly graded soil. Now I'm showing a grain size distribution chart. I'm just going to draw in 3 different grain size distributions. So the first one we can see with this blue line. Second grain size distribution I'm drawing in with this red curve, and the third grain size distribution we're going to draw in with a green line. Visually, we can see that the blue line has grain size distributions over a broad range, and so we would expect this to be a well-graded soil. The red line, there are very few grain sizes in this soil, and so we expect that to be poorly graded. And the green curve predominantly has 2 sizes of grains, so we would call this a gap graded soil. It also is a poorly graded soil. I will go over how we calculate the coefficient of uniformity and the coefficient of curvature. These are values that are used in addition to visually inspecting the grain size distribution to determine whether a soil is well or poorly graded. The coefficient of uniformity is calculated as the ratio of the grain size where 60% is finer by mass divided by the grain size where 10% is finer by mass. Then the coefficient of curvature is calculated where 30% is finer by mass squared, that grain size divided by the grain size where 10% is finer by mass times the grain size where 60% is finer by mass. When our uniformity coefficient is equal to 1, it indicates that all the grains are the same size. So we'd think that would be a poorly graded soil. If our uniformity coefficient is much greater than 1, the grain sizes span a large range of particle sizes, and that would be an indicator that our soil is well graded. However, we can't rely on our uniformity coefficient alone to determine whether or not the soil is well graded or poorly graded. So we also use the coefficient of curvature. If the coefficient of curvature is in a range of 1 to 3, that tells us that we have a smooth distribution or a smooth curve. So that would be an indicator that would tell us, hey, this is well graded. If our coefficient of curvature is less than 1 or greater than 3, then the curve is not smooth. And so that would support or indicate that this is a poorly graded soil. So the next thing we want to do is work on another example using the data from our grain size distribution that we looked at previously. So we have our grain size distribution that's given to us, and so now we want to find the uniformity coefficient, or the coefficient of uniformity, and the coefficient of curvature. First, we'll find the percent finer by is the 60% finer by mass grain size. So we draw a horizontal line from the 60% finer by mass, and then a vertical line to figure out what that grain size is. And that grain size is approximately 0.82 millimeters. We'll do the same thing for D30 and D10. So as we look at D30, using the green line to indicate the grain size associated with 30% finer by mass, come up with a value of about 0.39 millimeters. And then finally, our D10 looks like we have a grain size associated with 10% final round mass of 0.23 millimeters. So now we can calculate our uniformity coefficient and our coefficient of curvature. Coefficient of uniformity, D60 over D10. So we have 0.82 millimeters divided by 0.23 millimeters. So our coefficient of uniformity then is 3.6. Now to calculate our coefficient of curvature, that's equal to the D30 squared divided by D10 times D60. We have those values listed above. Well, let's rewrite this so everything's not scrunched up together. Again, we have D30 squared divided by D10 times D60. And when we do this calculation, we end up with a value of 0.81. Based on the information we were provided earlier, because our coefficient of curvature is less than 1, we would say that this sand is poorly graded. That concludes how we perform a grain size distribution, how we use that grain size distribution to calculate the coefficient of curvature and the coefficient of uniformity. In class, we'll go over a little more detail on how we perform a hydrometer analysis and determine the grain size distribution for those materials that have particle sizes less than 0.075 millimeters.